Straight-chain hydrocarbons are good solvents for a variety of oily substances such as paints and greases. This makes them particularly common in home products such as mineral turpentine, white spirit, petroleum spirit, and scheelite. These mixtures contain a combination of many hydrocarbons, so analysis requires them to be separated before the detection of individual hydrocarbons can be achieved. In this GC practical, we'll be analysing one such solvent mixture using gas chromatography. Two 25ml Class A volumetric flasks were cleaned using isooctane as a solvent. Both flasks were partially filled with solvent to ensure minimal analyte loss to evaporation during the subsequent weighing. One flask was tared on the balance, and 10 drops of undecane was added. The weight of this undecane was recorded as 0.1252 grams. This flask was made up to the mark with isooctane. In the second 25ml flask, 10 drops of decane, dodecane, and tetradecane were added and weighed. The decane, dodecane, and tetradecane weighed 0.1122 grams, 0.1250 grams, and 0.1300 grams respectively. This flask was also made up to the mark with isooctane. The flask with the undecane is used as an internal standard in the analysis, as undecane is similar to the compounds of interest and is not present in the mixture being analysed. The flask with the 3 compounds is the standard to be used in the analysis. The vial of the unknown already had 0.75 mils of the unknown in it. To this, 0.75 mils of the undecane internal standard mixture was added. To a second GC vial, 0.75 mils of the 3 hydrocarbon standard was mixed with 0.75 mils of the undecane internal standard. By ensuring the 2 vials had the same amount of internal standard, the height of the peak of the internal standard could be used to correct for any fluctuations in the instrument response between runs. The 2 samples and the sample of the acetone were run on the GC instrument. On the GC instrument, the sample carousel, autosampler, needle, and oven can easily be seen from the outside of the instrument. The inlet, split valve, column, and detector are hidden more deeply inside the instrument. GC operates similarly to other forms of chromatography where there is a stationary and mobile phase which facilitates the separation of analytes. In the case of GC, the sample is volatilized in the inlet and swept through the instrument by a flow of gas. The sample is split, so only part of the sample makes its way onto the column, and most of the sample makes its way into the vent. Once the sample makes it to the column in the column oven, the sample may stay as a gas or condense as a liquid on the walls of the column. Low boiling point analytes, such as acetone, stay in the gas phase and are quickly eluted from the column. Analytes with higher boiling points, such as decane, interact with the stationary phase as liquids and are retained, making them take longer to elute. The column in this case is a HP5, which is 95% dimethylsiloxane and 5% diphenyl siloxane, and has a length of 30 meters and an internal diameter of 0.322 millimeters. This phase can change the volatility of analytes due to the strong interaction between the analytes and the column. Once the analytes elute from the column, they can be detected with a flame ionizing detector, or FID for short. In this detector, the conductivity of a hydrogen flame is measured. When only hydrogen is present, the conductivity of the flame is low, but when compounds elute, they are broken into ions, which raises the conductivity of the flame. It is these ions that make up the detector response. In this practical, acetone is used as an unretained compound to be injected onto the column. By knowing the time it takes for acetone to elute and the dimensions of the column, it is possible to determine the volumetric flow rate through the column. The flow rate through the vent was measured using a burette filled with detergent. The time it takes for soap bubbles to raise 50 ml up the burette was recorded. By calculating the ratio of the volumetric flow rate of the split to the volumetric flow rate of the column, it allows the split ratio to be determined. In this practical, the GC was set up using the conditions detailed in the laboratory manual. The acetone, calibration standard, and sample were each injected 3 times to enable confidence limits to be calculated. Use the acetone results as the time for the unretained peak and the column dimensions mentioned earlier to calculate the volumetric flow rate through the column. The flow rate through the split may be calculated from the time taken to elute 50 mL of soap bubbles. You may require further information about response factors. Detailed information in example calculations of response factors may be found in the CVB202 GC notes.